Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. The recording you're about to hear is part of a series of interviews I recorded live from the O'Reilly AI and Strata conferences in New York City last month. I'll be sharing these interviews on the podcast over the next several weeks, and I'm sure you'll enjoy them. This time, I interviewed Diogo Almeida, Senior Data Scientist at healthcare startup Enlitic. Diogo and I met at the AI conference, where he delivered a great presentation on in-the-trenches deep learning titled Deep Learning, Modular in Theory, Inflexible in Practice. Diogo and I discussed the ideas he presented, which are centered on the data, software, optimization, and understanding issues surrounding deep learning. Diogo is also a past first-place Kaggle competition winner, and we spent some time discussing the competition he competed in and the approach he took to win it. Before we jump in, a bit of a listener warning. Our conversation gets pretty technical pretty quickly. I do try to make sure to summarize key points from time to time, and I really think that if you hang in there, I'm sure you'll learn a ton. Of course, let me know how you like this level of detail. I'll be including links to Diogo and a bunch of the datasets and other things that we discuss in the show notes, which you can find at twimlai.com/talk/8. Also, as is the case with my other field recordings, there's unfortunately a bit of unavoidable background noise. Sorry for that. And now, on to the show. All right, hey everyone, I'm here at the O'Reilly AI conference, and I'm sitting with Diogo Almeida, who just did a really interesting talk on deep learning, and he was kind enough to sit down with us and talk a little bit about what he talked about. Diogo, why don't you introduce yourself?
Cool. I'm Diogo Almeida. I work at this super cool medical deep learning startup where we work on giving like really accurate, really fast, really safe medical diagnoses. And this is something that we hope will completely change the world. Before that, in a past life, I was a mathlete. So I broke a 13-year losing streak for the Philippines in the International Math Olympiad. Was in the top team in the world at the interdisciplinary competition in modeling. And there's a website for machine learning competitions called Kaggle that I won first place on in one competition as well.
When was that?
This was in 2013.
Okay.
It was the cause-effect pairs challenge.
Tell us about that.
Oh, it was a very weird challenge where in most machine learning you have like tabular data.
Right.
So, like you have columns of features, rows of observations. And in this problem, your data was pairs of sequences. So you have something like altitude and like one observation is like altitude and height, and you have like a sequence of pairs of like which altitudes correspond to which height in some unordered manner. And the idea was, given this, you're supposed to predict whether altitude causes height or height. The altitude and height were the same thing. I meant altitude and temperature.
Right.
So you were supposed to predict if altitude causes temperature, or temperature causes altitude. It's obviously that altitude causes temperature, right, for us. But there's a lot of like very complicated tasks that we don't know the answer to. And it's kind of like the basic task is to, if you know the saying, correlation doesn't imply causation.
Right.
It's supposed to do the opposite of that. So you're supposed to figure out how the correlation implies causation. Okay. Which is, it's extremely useful because you have like lots and lots of observational data.
Right.
It's very hard to have like a controlled study. So the more accurate we can get a view of the world from purely observational data, the more we can either have informed priors before running the controlled study or figure out how to order the controlled study in an appropriate way.
Okay. And is this also the kind of analysis you would use for like a root cause analysis or something in like an IoT use case where you've got all these observations and you're trying to figure out what the underlying condition is? Or
I'm not as familiar with that. There was traditional statistical work, and there actually was a background for this topic, but I kind of didn't pay much attention to that because I kind of went my own way, and it was much more for fun than for winning. Yeah. And winning was a very nice side effect.
Nice.
And I went switched to a much more like software-oriented way of just like build a really complicated, powerful model and have it solve this based on like rather than like hand engineering stuff. Why not just like automatically engineer a lot of informative variables and then solve it with that?
Okay. So can you walk us through the process? Like, how did you formulate a methodology for attacking them? Was this your first Kaggle competition, or had you been doing them for a while?
My first serious one. I've done like one or two before that I didn't really spend much time on.
Yeah.
But like, you quit like after 2 days because it turns out your teammates weren't useful or something like that. So I have like played with it before, but I've never really gone all out until this one. So my methodology was, well, some background is that there are like statistical tests that people use that did very well in this task. Okay. And, that people used to use in this task. And to put it roughly in perspective, these got like 0.6-ish AUC. So if you see a paper in Nature or Science about a new test for causality, it probably gets around 0.6-ish AUC.
Okay. AUC, for those that don't know, is area under the curve, and that's a performance metric?
Yeah. So we were solving a ranking problem. Okay. Or we were trying to rank the outputs, given that we know which ones caused each other. It's a little bit of a complicated metric because we actually had 3 output classes. So we did like a bidirectional AUC, but that doesn't really matter much. And so these tests, we had like 0.6 AUC. They're roughly a single feature because it's just the prediction. You extract it directly from the data. Most of the other competitors in like the top 10 had, tens of features or something like that. And the second placer, I think, had like a whooping like 100-something features. Okay. And I had 50,000. So, wow. So what I did was I found like a very simple way of determining causality, which would be the rationale would be if X causes Y, then Y is a function of X. There's noise in there somewhere. Right. So roughly you can tell how good one is a function of the other based on how well they can be approximated by functions. And this is kind of like a very vague like recipe for how to create these features. But the idea is rather than hard coding statistical tasks like like add a Gaussian, integrate this thing out, whatever, I just figured that we have an entire field of curve fitting which is called machine learning, right? And these are often like built after very natural priors. So the idea would be try like a ton of machine learning algorithms, all of the ones that are computationally feasible. Try different metrics for what fit means, because fit is it's kind of like not like a very exact term, right? And like these are all of the features now. Throw them all into like big boosted decision tree. Train this thing for a week on like a 50-core machine, and then take a nap the entire time. So that was roughly my solution.
Wow. And so the solution was primarily based around the boosted decision tree, as opposed to some super complex ensemble or something like that?
Yes, actually, it's a weird story that for this competition, I was so far ahead for almost all of the competition, I didn't even try. Okay. So what was it? Like for basically everything beyond the last week, like maybe a month or a month and a half before that, I even started the competition late, I was like so far ahead that the gap between like me and second place was like the equivalent of like, second and like 15th or something like that. Oh, wow. So I was like feeling really confident, and I actually stopped paying attention to this because I felt that like, oh, this is going to be easy, right? But then during the last week, people started sharing their solutions. Like I only got 10th or something. Here are the features I used, and all of a sudden, like everyone started rising. Okay. And this is definitely
basically by creating ensembles of everyone else's solutions.
Like people like kind of hinted at I think it was only one person, but like they had like a lot of good stuff in there that other people started using. Okay. And once people were getting performance, they like make more of it or something like that. So people are starting to rise, right? Right. And like haven't even ensembled this far. And I unfortunately had a model that took a week to train, like I said. Yeah. So, and I only had 1 week left for the competition. So I decided that I tried like a few last minute attempts at ensembling, but nothing beat my super big 1 week long model. Okay. And so I just stuck with that thing, and that ended up actually winning. And it actually was very scary because people ended up passing me. On the training on the validation leaderboard. Yeah. But in the test leaderboard it was completely flipped because they
overfit.
Yeah, they had like hundreds of submissions, while like my best submission was like my sub-10th. Because
Okay.
like it was a very like hands-off competition for me.
Yeah.
I cared about it a lot, and I wrote like lots of software that was I thought nice. But like I really thought that would have been like an absolute slam dunk.
Okay.
So it's exciting though.
Okay. So where did the 50,000 features come from?
So you can imagine like exponential growth when you're just trying like every combination of this with every combination of this.
Yep.
There was like every combination of metric that I can think of, every combination of machine learning algorithm that was like computationally tractable. There was like symmetric features, so you could like augment your thing with like difference features because like it doesn't matter which X or Y is, right? There was a nuanced thing that I don't normally explain when I talk about the competition, which is not all of the input was numerical. Some of it was categorical.
Okay.
And like you just can't like throw categorical data into a numerical algorithm, right?
Right.
So it becomes actually a complicated problem of how do you compare
So
numerical
there's just
to
different
categorical.
ways of calibrating your bins
Yeah.
or something like that.
Well, I mean, you can. It's very easy to convert numerical to categorical,
Yep.
but you lose a lot of information from
Yeah.
that, right? So what I did was I did different ways of converting from, like this is like a categorical numerical pair metric.
Yeah.
So this stuff like convert numerical to categorical via like clustering or binning or something.
Right.
And then when you want to convert categorical to numerical, you do something like the PCA. Like get the first principal component or something like that, or projection to the first principal component. And I basically are just looping through all of these things. So you can imagine like a lot of nested for loops.
Okay.
In the end, I had a bunch of them, so like that ended up with like 50,000-ish. And I also
Wow.
skipped a detail there, which is I also used a feature selection algorithm in order to like make it a little bit smaller, which
Okay.
helped performance a bit, but it ended up not being important. So
Okay.
I usually omit, but for the sake of clarity, that was also done.
Okay. Wow. That sounds pretty cool. And now that was a little bit of a digression, I guess.
Yeah, complete digression. Yeah, interesting story though.
Yeah, absolutely.
It's actually generalized to new problems as well. I believe the competition organizer was applying it to some sort of biology problems, and they were showing that it actually predicts causality on that as well.
Oh, really?
So, yeah, hopefully that kind of thing could be really useful.
Oh, nice. But what you were talking about here was deep learning.
Yep. Yeah, that was not deep at all.
And I didn't catch all of your talk. I caught the last bit of it, but it seemed like what you were going through was kind of a bunch of war stories, lessons learned. Like, you hear a lot about deep learning, but there are a lot of things that people broadly believe about deep learning that actually are false. Mm-hmm. And why don't you explain kind of what your intent was for the talk and kind of walk us through, an overview of what you presented.
Cool. So the way I see it is like there's these two competing views on deep learning, like extreme views, which is deep learning will solve all our problems, and deep learning is complete garbage. Or, sorry, it's all hype. That's kind of exaggeration, but maybe for exaggerating views you can say that. And there's evidence for each of these views. Like there's some amazing results of deep learning. There's some extremely poor results on deep learning.
Right.
And the idea is that like these are not as informative of the stuff in the middle. So the idea was like if you draw all this evidence in like this one-dimensional plane, and you like try to like draw like a max margin hyperplane, you might get like this interesting decision boundary, because like this is where the interesting stuff lies. Like this is the stuff that's going to be moving slowly over time if deep learning is doing well, right? Or the other way, if people are starting to like find all sorts of failure cases. Mm-hmm. And the idea would be if we talk about like these examples and like the edges of our understanding or the edges of our everything, or like edges of like all of the things that are limiting deep learning nowadays and like keeping us from solving all of our dreams, that can hopefully give people an impression of like what everything else is like, because it's like just very extreme on the other ends of the spectrum. And I feel like that's just not very much talked about, because like you said, like a lot of people are on the deep learning hype train, or kind of being sad at home and like being grumpy because now all of the questioners are silenced, right?
So if we kind of map out what the corner cases are and the failure modes and things like that, it'll help us push forward our understanding of this thing is the basic premise.
And kind of like acknowledging it also helps. I don't think what I did was the greatest acknowledgement of it, but I think it was a more thorough one than I've seen before, and realistic especially, in that I think that sometimes just understanding your problem really well really helps you to solve that problem. So I know now that, I mean, like I do research as well, and this stuff's very important to me. And by looking at it from like kind of a higher level, I can kind of see better, like this seems like something that looks really promising to me, or this doesn't seem promising at all, right? Like, for example, one of the problems with deep learning nowadays is everything's very local, right? Like, you get
local in what sense?
You use the gradient, right? Or maybe higher order derivative things. But for practical purposes, you use the gradient, and this can be insufficient for some applications, right? And it makes you by going to a higher level. Maybe I can start with a lower level, right? Like SGD doesn't work for my spatial transformer network. This is unfortunate. Like, let me try Atom, let me try RMSProp. But if you go to a higher level, you realize that the problem is the local learning in the spatial transformer network, not necessarily the gradient descent. So
tell us about spatial transformer networks and what those are.
Yeah. So this is just one example I use of a kind of network that it's very easy to see the issues of local learning with. It's very nice because it's a differentiable network. It's very easy to see exploration problems in reinforcement learning domains. But this is one that you have a derivative of, and it should be easier to optimize, and it is. But you sometimes don't get what exactly it doesn't like fulfill its full potential.
So are you kind of seeing that there are a lot of people coming into the space that try to throw deep learning at a given problem? The common way of solving it is using stochastic gradient descent, and they don't really think about how that's working, and that it's finding a local optimization, and there are some problems that for which they get kind of stuck in that local. And
that is unfortunately the case. Like, I have seen many people introduced to deep learning who think that let's stitch together an architecture that's differentiable, and then bingo bango, call it a day. We've like solved problem X, right? Like they realize the the limitations of requiring large data sets, but they think that that's what it amounts to. And I think very oftentimes it doesn't. So back to spatial transformer networks, what they are is basically, instead of like a single network that learns how to classify an image, you have two networks. One of them learns which part of the image to look at, and the other part takes what that network looked at and does the classification on it. And this is a huge advantage because a lot of the times your input image might be really large and you don't want to run the network over all of it. It might have like unnecessary information. It might be really useful to like co-localize, so like have the where as well as the what. So there's really good reasons to use this. And in fact, for medical problems, if it worked well, I would use it for everything, number one. And number two is, if it worked well, I would use it for every computer vision problem. Because what these spatial transformer networks can do is not only find the region, but it can also transform the region into a canonical location. So rather than having to learn filters of like cats at every orientation, you might have to learn filters of cats at only one orientation, which like would result in like much better data and parameter efficiency. But back to the issue here is that you have these two networks that they're not competing, but they're working together, but they're only using the current other network as its source of signal, basically. So if your classification network gets really good early on in training, your localization network gets stuck in this optima, right? Because like if it changes anything at least a little bit, your classification network will do worse. So like the gradient tells it like, hey, just stay where you are, you're pretty good, or move you around a small region, right? Which might be very far from the intended purpose, right? Of like correctly like zooming all the way into the thing you care about and like rotating it a lot. And on the other hand, if the spatial transformer network converges early, so imagine the classification network is garbage, it might zoom into like regions of the image that are just independent of the class, but makes the classification network tends to perform a little bit better on. So it might, like, for example, if you're trying to classify kinds of dogs or like ImageNet, and it turns out like your classifier starts out like just being good at telling grass means dog, and the localizer notices and like just zooms into the grass, right? Like goes zoom grass, and basically you've cut the dog out of the image. And the moment you've cut the dog out of the image, you get no gradient signal. And when you have no gradient signal, you're stuck there forever. And this is a problem that people just don't really like to acknowledge in networks, right? Like that's actually a very complicated relationship, because now you need to like maintain a balance in all of that. And I don't think people even know how to do that. Like, people don't know how to do it with generative adversarial networks either, which is another example I gave of this.
Yeah. Huh. So what was the overall structure of your talk?
So the title of the talk was Deep Learning, Modular in Theory, Inflexible in Practice.
Uh-huh.
So I first wanted to talk about the successes of deep learning, not get any, or rather to show that deep learning is very modular and it can do a lot of things. And, get them into the mode like, wow, we can solve everything. And I actually think that I had a somewhat bold claim to end that first part, which is that today's deep learning components can solve any problem, any like computable problem, if you ignore the practical aspects, which would be, I mean, I think it's interesting to point out, right? Because then now that you isolate that, you know that the practical aspects are the issue, right?
Right.
And those practical aspects are data, software, optimization, in probably order of difficulty of how to understand them. And the latter part of the talk, I talked about these issues with deep learning, like specifically data, software, optimization. And I had a final section on understanding, just because I wanted to point out that while understanding is not necessary for like getting things to work, which maybe is what we care about, the understanding is very necessary to make progress, right? And it's amazing how little we understand about anything.
Well, let's come back to that and maybe walk through the different sections. So data, walk us through the points that you were driving home around that.
Okay, so from a super high level, it's that neural networks are extremely data inefficient, and they don't have to be that way. And data efficiency is the root cause of all problems, because if we were data efficient, the size of data sets wouldn't matter.
Right.
The data sets we use are kind of flawed in that, like, they have known issues that researchers know about.
Known issues like they're noisy, or like what kinds of known issues?
Like Pantry Bank is a very small data set, therefore making bigger networks is not very helpful because it overfits. Therefore, you should generally only publish regularization research on it or something like that.
So you're referring primarily to kind of the known data sets,
they're the commonly used data sets,
that kind of thing.
It's the kind of things that like the mainstream deep learning researchers publish on to convince them, hey, I have something cool, use my thing.
Right.
And that is, I mean, it's important, right? Like, the alternative is publishing a data set no one knows about, which is also very hard to get any information from. But
one has kind of it's almost like a reproducibility kind of issue, where there are elements that are inherent to the data set that, drive towards or require a certain class of solution.
Yeah, it's a horrible state of affairs where, like, you need to, like, if you read a paper, the paper usually has the high level. It doesn't have all the low level details. That's what the code's for. And you implement the paper exactly as it says, and it gets not anywhere near close to what they had, right? And you're like, yo, what the F? And then, you email the authors, maybe they eventually read the source code, and you run the source code because you don't believe them, and you're like, wow, it just reproduced exactly what the author said. And it turns out, like, it just has like a bunch of magic hyperparameters. Like, you set, L2 regularization to this. You need this learning rate schedule for sure. Use this optimizer, and also preprocess your data set in this way and sample it in this way. And like, these are all things that you really want to be robust to. Right. And you just aren't, right? Like, it's a very unfortunate like aspect of the world, right? Like, you're put into this position where if you don't if you don't play the game, you never get state-of-the-art results, and people don't listen to you. If you do play the game, I mean, some people listen to you, but some don't because they know the game. But then, like, it's the only way to get people to see your thing.
And by the game, you mean in terms of the researchers, like, they're driven to publish, win in the competitions for whichever data set that they're looking at. Is that
usually
the game
not competitions, but it's usually like you want to get people interested in your papers.
Yeah.
And it's very different if you just didn't care and you wanted to publish interesting things, right?
Right.
But if you want to get eyeballs, sometimes, like, unless you're already a respected person, it's kind of what you have to do. Yeah. Right. So, sometimes that kind of thing is important. I think that it's kind of a very qualitative thing, which is unfortunate in the data world, that it gets to get a feel of a data set, like when this data set's starting to get like really overfit, that perhaps it's not useful anymore. And I feel like some researchers like qualitatively feel that about like CIFAR 10 and CIFAR 100. Especially CIFAR 10. I'm not 100% sure about CIFAR 100 as
And
much.
what's that data set?
This is a data set of 32 by 32 RGB images.
Okay.
It's a popularly used baseline because it's a very small baseline.
And images of anything in particular? Or?
CIFAR 10 has 10 classes.
Okay.
So 10 common classes. And they're... it's a popular data set because it's a really small data set, 32 by 32 images. You barely see anything. And it's not MNIST because people have like basically decided like MNIST research is not enough. So like they just don't listen to MNIST research at all, right? And it's starting to be that way for CIFAR 10 just because we're getting to be so good on it now.
Okay.
And yeah, there's just known limitations that makes it hard if you have a genuinely good result to tell people that you have a genuinely good result. Especially because like as you scale up, like it's also very computationally demanding, right? So,
and you describe the data sets as being overfitted.
Oh, for sure.
Which elaborate on that, because I tend not to think of data as being inherently more the algorithms.
The community is overfit to data set, not even the algorithm itself.
Oh.
There's actually this cool test that someone did, I can't remember who, where they showed us like 4 pictures of images, and they asked like these are the 4 data sets, or sorry, maybe not. They said like, do you know what data set this picture's from, this picture's from, this picture's from, this picture's from?
Right.
Like many people did. Like CIFAR is a very canonical data set.
Right.
There's a places data set. There's a large scene understanding one.
Right.
And there's ImageNet, which is like more general.
So you're basically saying that
if someone can recognize
we know
the
these data sets so well, we're designing solutions to them that are not generalizable or not adequately generalizable.
And like people have actually reported, like negative results are generally not reported as much because there's just so much of it, right? It's a very empirical field. So maybe this is uninteresting now.
Right.
But this just happens so much. Like people have noted that the inception architecture seems to work much better in ImageNet than it does in other tasks. And it is a pretty complicated thing, right?
Right.
So maybe that makes sense. Or I've had friends that I talk to. I'd hate that a lot of my references are friends, but there's like the field moves so fast that like sometimes even archive can't keep up, which is I think super awesome for being in it. And anyway, they chat about sometimes how ResNets oftentimes don't work for their computer vision architectures, right? Or one of the best practitioners of using ConvNets, a friend of mine, Sander Dieleman, he works at DeepMind. He has not been able to find batch norm to work for him. And I find that to be really interesting. Like, is it because all of his other parameters are tuned to batch norm? Is there something that he's solved that batch norm solves also that is not necessary? Is he just wrong? Honestly, I don't know. But I think that there's a bunch of cool stuff there that maybe we can figure out, right? And
is this issue inherent to deep learning, or is it just the approach we've taken?
I would argue that it's not even an issue in deep learning. It's actually, like, maybe we can look at the bright side of this, of like, it's a miracle it even works. So, going to the understanding topic.
Right.
There's, as far as I know, no practical theory in deep learning. Like, there's nothing that can actually like guide us to understandings. Like, there's what I call stories. Like, every paper has like a high-level story of this is why I think it works.
Yeah.
And if you like really try to vet the story really well, you can like very easily like disprove that. And I know of no story that's like 100% bulletproof. So I'm willing to make that claim. And so we have these stories, and like they guide people, but they rarely work out as useful tools, unfortunately. So what we have instead is empirical results. What we do is we want generalization. Generalization is kind of like a lofty concept, and we don't really know, like, it's not like you can, in like traditional statistics you can kind of do that, but like in deep learning it's just much harder because you have so many parameters. Like you can't really measure, well, you can measure the VC dimension, but it's so big that it doesn't matter. There's a lot of things that...
What's the VC dimension?
I probably would screw this up, but I'll give you like my best like first order approximation of what it is. It's roughly how powerful your model is. So it kind of corresponds to like how much data you need in order to get generalization.
Okay.
So like very curvy, powerful models have like very high VC dimension, which means that you need a lot of data.
VC doesn't stand for very curvy, does it?
No, it stands for, I know the V stands for Vapnik.
Okay.
And the C stands for another person's name.
Okay.
So generalization, like in a, like in the very old school machine learning sense, a sense that I don't think we'll come back to personally. Like you could have bounds on like how much data you need in order to get like this epsilon difference between train and test and stuff like that. And that's just not something that's going to happen in deep learning. And as long as we keep using deep learning, we're probably not going to get that.
Right.
So what we have is empirical results. And with these empirical results, we just have a bunch of experiments and a bunch of data sets. And we show like, it seems to work on the data sets we've tried. Hopefully it works in everything. And so like this is where you might see it as a pro, as a con, but I see this as a huge positive of deep learning, right? Like it's actually super cool that it generalizes, right? Like you can get a new computer vision task. I use computer vision because like that's one of the easier domains, and you can have a ton of data, and you can just generalize. You can use it to generalize. You can use ImageNet features to generalize in that. That's just not something that makes sense, right? I mean, like if you look at it from like a really strict perspective of like, there's no guarantee that this should work, but it tends to work. And that's really interesting, all right? And I think that there's something about deep learning that allows it to generalize so well. You can even generalize to domains that you've not even trained on. I think that there's been some work on generalizing ImageNet models to cartoons. And like even like cartoon drawings of the things that they were classifying sometimes activate, or there's something related to that.
Yeah.
So yeah, it's a wonder of deep learning. There are some experimental results that try to explain after the fact why things work, but without being falsifiable, it's questionable how useful it is. So perhaps maybe deep learning is exploiting some of these kinds of explanations. There was a recent one on physics that deep learning is the class of things that deep learning is very good at fitting are a very natural class of functions. Therefore, since deep learning models only can efficiently fit a small subset of the function space, but that happens to be like very common, like based on physics, kinds of functions that would occur.
Okay. So you started out talking about data and that overfitting problem, and then tools, was that the net, or software? Software.
There's two more things in data, though, which is that the data we have, which is problematic. There's the data data we have and we use, like data sets. There's the data we have that we don't use. And there's like tons and tons of data that we have that we don't use that I think that we just don't know how to use well. Unsupervised learning, multitask learning, transfer learning we kind of use, but we don't do very smart things, I think. And even like there's implicit stuff like the trajectories of the networks that you've passed through. Maybe there's some interesting information there. And the last kind was the data that we don't have that we need, like for example measuring these things that we really care about that we are just missing right now. Like we have no way of measuring long-term dependency, like how well networks capture long-term dependencies. We don't have like a general RNN benchmark. We don't have a good benchmark for visual attention. We don't have a good benchmark for hierarchical learning. Like how do we even know if we're learning hierarchical stuff, right? Do we want to learn hierarchical stuff? I don't know, but like I would think that if we want to learn something, having a benchmark for it would be really good, right? So that was roughly it for data. From a software perspective, it was more about like how the tools we use nowadays really limit what we can do, and like every tool is flawed in some ways. This hits home for me personally because I'm a software engineer. And I want to use really good tools. You mean TensorFlow doesn't solve every problem in the universe? No, not yet. I think they introduced some really good ideas. They definitely brought something to the table. But it alone isn't enough. It might like I think better things could be built on top of it. I don't think that it's the low-level components that are a problem, and I actually don't think like hardware is that big of an issue, like as big of an issue that people make it out to be. In theory, in practice, if you really want state-of-the-art results and things, sometimes that's needed. But there's like higher-level problems that you can solve without hardware. So the idea behind software is that you can like very like easily see situations where the software we have actually prevents us from doing what we want to do. So I think I have like 2 examples that really resonated with me were that an example of bad software is when it's easier to explain in words the technique than it is with code, because ideally you want to like express you want like the flow from ideas to code to be really easy, and the flow from ideas to words is generally pretty good, and that just means like you have a bottleneck in like words to code, and maybe it's a reality of life that it'll never be that simple.
Did you provide a specific example?
Yes, I had like a list of like many examples of like different kinds of tricks that are hard to do in various frameworks. So depending on the framework you do, some things can be kind of difficult. So like for what is it? For
so when you say tricks and frameworks, the basic idea being, kind of the the research edge. I did see that you put a lot of papers. You were just showing a lot of papers, which is great, documenting kind of where the ideas came from. So in the research, we're introducing all these various tricks to improve solvability of the deep learning networks, and it's not, what I'm hearing is the tools are, on the one hand, great. They're raising the level of abstraction and making this stuff, more easily adoptable, but that also prevents us from implementing some of these tricks, which have to be plugged in at lower levels.
Yeah, exactly. So when I mention trick, I use that as a general term of like this like one unit of thing that you do to a neural network. Like you can think of layers as tricks, but tricks being more than just layers. Like for example, an additional regularizer might be a trick. Or doing, like they could be pretty complicated, I think. Like doing unsupervised pre-training might be a trick. And the argument that I would have is that no framework makes everything really easy. And easy in this sense is that I would ideally like it such that everything just gets solved for me. Like I would be able to like this is probably not going to happen, but we can get closer, right? Like I would like to express like very declaratively like what I want this neural network to be. Like literally like take this neural network in this database, apply this transformation, run this transformation, do it on this train on this training set. Like I want it to be that simple. And I don't think it can be, but like striving towards that I think is good.
Sure.
And like a lot of the frameworks like TensorFlow doesn't support a bunch of the things. Like it makes it a large number of lines of code in order to do something rather than few. So what would be an example? Like batch normalization is like a pretty simple thing, right? It's actually not a very simple thing in terms of implementation. But like many frameworks can do batch normalization very, very well. Like Torch can do batch normalization amazingly because like they can just implicitly keep its state. And in Torch, like each of the nodes applies its updates on its own, like when flowing through the grad and like applying the updates. So that's very good. But TensorFlow, for example, like in order to apply batch normalization, you have to do quite a few things, right? Like you need to create like some state for, if you're doing the rolling mean approximation, you need to create some state for the mean, some state for the variance. You need to make sure to like apply the updates to this thing. You need to only apply the updates at training time. And then it becomes like much more complicated than just like calling a layer on something, right? Depending on how you wrap it, of course. But it like this kind of thing is just a layer in Torch, right? And like every framework has its trade-offs, but I just don't think that we are at like the efficient frontier yet of like this is like I think we can get benefits for free basically. And I actually have written a few libraries that that try to get these benefits for free, and I think they've been pretty successful. I'm still experimenting with them because I think there's just so much to do there, but it's an open problem.
And are these libraries, are these standalone frameworks or libraries that plug into other existing frameworks?
Mostly they go on top of Theano or TensorFlow.
Okay.
Because I think that they're actually, or both. I think that they're both like very good baselines. I'm a big fan of the computational graph. I think the design of Theano is actually like quite excellent. I'm a huge fan of Theano and its developers. It has the downside of distributed computing. But I think that its abstraction level is actually quite good. Like, it can capture that abstraction level very well. Its optimizations are like things that I probably wouldn't do by hand anyway, so like you get them for free. It's a very, I'm more focusing on Theano. TensorFlow is similar, but it kind of has a mix of abstraction levels. So I'm focusing on the low level aspect. I think those low level aspects are actually like quite good. Like, they might actually be on an efficient frontier of trade-offs, like trading off like usability versus like
flexibility or
flexibility or performance. And I think that's like that's just one view, right? Like use a have a computational graph, have like all of the basic operations in there. Optionally use an optimizer in order to do that. Like, another view would be like the torch or cafe-ish view, where you bundle up the pieces of functionality that have a lot of like the highly optimized pieces, right? And that's the view you go for max performance, which I think is also very different philosophically. But there's nothing wrong with either of these views, so I'm fine building on top of that.
Just knowing what you're using.
It's more of the level and how you construct the computational graph, which I think should be independent of Theano or TensorFlow. Like, these are just different levels, right? Like, you could have like a really nice low level thing, but change the high level thing on top of it, and it should be fine. Which is why I'm not the biggest fan of TensorFlow's like many different abstraction levels, and I think all of the best people I've talked to who use TensorFlow, they kind of only use a little bit of it, and they think that a bunch of it is like, it's not the greatest, but I don't care, I'm not using it.
Okay.
And like, it's at those high levels that I think is very interesting. And like, that's also where the user interacts with it, right? Like, if you're having code interact with code, it doesn't matter. You can have like the ugliest interface in the world. Like, your compiler can just, switch things around and all of that stuff.
Okay. So data, software, what was the third piece? Optimization.
So I touched a little bit into it with local learning.
Yeah.
And Andrej Karpathy had a great quote, which I can't remember off the top of my head, but it roughly goes along the lines of that neural networks only do memorization. They don't do thinking. And this is problematic because this is already not his quote, but this is problematic because we'd ideally like them to think. We want them to do like cool, complicated things that like blow our minds in their coolness, right? And they do blow our minds already, but perhaps those things were simpler than we thought.
Yeah.
And what's going to happen when we want to do something pretty darn complicated?
Yeah.
Right. Like, we'll see, right? Like, there's some tasks that we think that would require some pretty complicated levels of thinking in order to do. Perhaps playing StarCraft, you need to like think many moves ahead and imagine what the opponent's going to do in order to like take actions, and neural networks are not very good at imagining what to do yet. Maybe that will change, but we'll see. And Andrew Ng likes to say that as a heuristic of what neural networks can do is anything a human can do in less than 1 second. But I mean, if that's a hard limitation, then there's a lot of tasks that take more than 1 second for people to do, and will this solve general AI for us? Maybe not, like when you phrase it that way, right? So, and it should be possible, right? Like, it's modular in theory. Like, you can just have architectures that, given a magic set of parameters, would solve that task. So the question is, how do we do that, right? And there's just many tricks on that. And I talk a little bit about the downsides of local learning, how we don't pay attention to exploration in supervised learning, and like mostly it's pay attention reinforcement learning, but we treat it as like obviously the plain, like, there is some implicit exploration because you're using stochastic gradient descent, so your gradient's noisy, but roughly if it wasn't noisy, you'd be plopped on a point and you just hill climb down some direction and be stuck there, and like, you don't even know how good of a solution that is, right? So that can be, I don't know, like, that can be very unsatisfying, because if the answer is, I mean, this goes back to what I was talking about, like, in terms of limitations, like, maybe local learning just can't solve this, right? And that would be super duper unsatisfying, because local learning is like our most scalable learning algorithm we have, right? Like, using gradients is really, really good for training lots of parameters. Like, we're gonna have to make like a lot of different plans if we want general AI without gradient descent. So yeah, we're gonna have to figure it out, or we're gonna have to figure out tricks on how to do this better. Maybe tricks for more principled exploration, and maybe this will make it such that these won't be problems anymore, or at least or we'll find much harder problems, right? There'll hopefully always be problems. And that's what keeps the field going, right?
Yeah.
But hopefully they're not intrinsic to the way we do optimization. And people are making better optimizers.
Yeah.
Even though it's quite slow, the progress.
Right. So data, software, optimization, and understanding, and we talked a little bit about that earlier. Yeah. Are you going to post your slides up somewhere?
Probably. I think that, I think the O'Reilly people put the slides up somewhere.
Okay.
But they haven't asked me for the slides yet. I think they're supposed to do that after the presentation.
Okay.
Which is probably good since there was like last minute editing going on. But it'll almost certainly be up somewhere.
Okay. And how can if folks want to learn more about what you're up to or find you, do you have a GitHub or Twitter or?
I do have a GitHub. Even though that's probably not a great way to contact someone.
Well, not contact, right?
GitHub.com/Diogo, Diogo 149.
Okay.
And probably email would be the best way. This is something that I love chatting about. It would be Diogo at, oh God, my company name's hard to spell. Enlitic, which is ENLITIC.com.
Okay. Great.
Cool. Thank you.
Awesome. Hey, thanks so much. All right, everyone. That's it for today's interview. Please leave a comment on the show notes page at twimlai.com/talk/8 or tweet to me at Sam Charrington or at twimlai to discuss this show or let me know how you liked it. Thanks so much for listening and catch you next time.